Ladies and gentlemen, I think we can get started. The snacks will be served shortly, and my apologies for the delay. So without any further ado, let's begin. Ladies and gentlemen, my name is Armagan Al-Haq. I am the Managing Director at the Waterloo Institute for Sustainable Energy. I work under the leadership, as you guys know, Professor Claudio Canizares. He won't be able to join us because he's teaching a course outside Canada. I will start with the territorial acknowledgement. The University of Waterloo acknowledges that much of our work takes place on the traditional territory of neutral Anishinaabe and Haudenosaunee peoples. Our main campus is situated on the Haldimand Tract, the land granted to the Six Nations that includes 6 miles on each side of the Grand River. Our active work toward reconciliation takes place across our campuses through research, learning, teaching, and community building, and is centralized within the Office of Indigenous Relations. It's my honor and privilege to introduce our guest speakers for today. As you know that we have 3 lectures. The first one has 2 speakers. The first one is Dr. Ricardo Alvarez. Thank you so much for joining us. He received the degree in electrical engineering from the University of Chile in 2005 and the PhD degree in electrical engineering from RWTH Aachen University, Germany in 2016. He is currently associate professor at the Technical University Santa Maria. He is also a researcher at the Solar Energy Research Center and director of the PhD program in electrical engineering at the same university in Santa Maria. His main research interests include power system planning, operation and optimization, large-scale integration of renewable energies, and the use of artificial intelligence in power system applications. I would also introduce the second speaker for today, Pablo Otizia. He is a master's thesis student at the Technical University in Santa Maria. He has experience working in the Chilean energy industry, namely in the Chilean National ISO and in Translec, which is the largest transmission company in the country. His work focuses on transmission, network planning, and the optimization of power system through machine learning. He is currently working with the University of Waterloo in a joint project for solving transmission planning problems with neural networks. So ladies and gentlemen, please put your hands together for our first speaker for today. Thank you.
Thank you very much, and thank you especially Merdad, Professor Merdad Pirnia, for having me here as well as my colleague in this joint research project. And I'm very happy to give you this lecture. It's about power system expansion process from the way we plan it until we really build the transmission lines, which in most countries, it's a challenging task, yes, because of regulatory issues, because the planning process, it's complicated. I'm not sure if the presentation is there. So it will be interesting to see how different or how similar, what are the similarities and the difference, there it is, between Chile and Canada is, and how I will present you the good ideas that we have had in the past year to face this issue. Some of them worked, some of them didn't work. So I hope that we can turn this into also a conversation. If you have questions, if you have comments, what is similar, what is different, please go ahead. So a little bit of background. This is the very illustrative picture of the main Chilean power system. The system is very longitudinal, yeah, with long transmission lines, with interconnection between areas. This is around 1,500 kilometers, and we have significant renewable resources, but concentrated. In the north, lots of solar power. In the south, hydropower. Along the coastline, of course, we have also conventional generation plants, and along the coastline we also have some wind energy. And in Chile, our generation matrix grew very fast toward renewable energies in the past years. And the problem, though, is that the building transmission lines to meet this integration requirement, it's difficult. It takes several years in Chile, and it's becoming increasingly more difficult nowadays due to social and environmental concerns. And the consequences that we face, okay, the renewable generation integration was very big, but we had increasing congestions, renewable curtailment, marginal costs going down to zero every day, especially during the solar hours, and among other issues. So I'm not going to speak more in depth into this situation, because I guess it's about the same in every country. So I'm going to tell you to speak about how is the Chilean process for building a transmission line and how we dealt with all these issues. And to provide a background, it's important to present some basic regulatory principles so that you understand how is the Chilean electricity market how it's developed. So we have a long-term financial bilateral financial market where we have long-term bilateral contracts between generating companies and free customers, meaning industry, industry or large demands. And we also have financial contract between generation company and distribution companies, and the difference in both cases are bilateral contracts, but the difference is that here is through auctions that occur every 2 and 3 years, and new capacity is required for these auctions. So in order to sustain long-term adequacy, every generating company that wants to compete in this auction, it needs to say, okay, look, I want to bid for this, but I will build a new generating unit only because of this auction. If it get done, then he needs to build this generation. So that's how we try to sustain this long-term adequacy. Then we have, sorry about that, the generation dispatch, which is defined by the market operator, which is the same entity as the independent system operator. And our generation is done, it is centralized under minimum cost criteria. And for that, it uses audited cost provided by the generation company. So the market operator solves an optimization algorithm, optimization problem to minimize the cost, the operating cost of the system, and disregard to any of the contract or of the bilateral contract. They don't care about they do not interfere with the generation dispatch in our case. And of course we have a market for ancillary service to ensure operational security. And so this is the picture of our energy and power market. I did something. Okay, so what are the what are our interconnection guidelines? In principle, by law, we have an open access to the transmission system, regardless of the ownership of the infrastructure. Who owns the transmission line, who owns the substation, that doesn't matter. You have the right to be interconnected to the main system. And we have a transmission pricing based on a postage time approach, which means that the customers do pay for that. And the reason for that, this has two benefits and drawbacks. The benefit is that it incentivizes the incorporation of new renewable sources, which are bound to be in a location of the system with where the renewable resource is. So it doesn't matter, since they don't have to pay specifically for the transmission pricing, since the customer pays. They are incentivized. In this way, we incentivize the incorporation of new renewables. The drawback is that the delays in the transmission expansion have increased the congestion, the renewable curtailment, thus threatening the proper return of investment. And the reason is that since the since you do lose a little bit the location price for interconnecting new generating units. So this is more or less the drawback. It has worked for us as in this case. So that's the picture in Chile right now as regarding to the interconnection guideline. And this is the main part of this talk, which is, okay, how is the expansion process works in Chile? We define a new process that started in 2017, and this is in a nutshell, but you can see that this process involves several entities in Chile. It starts with the Ministry of Energy, with where they define a long-term energy planning. So the long-term energy planning developed by the Ministry of Energy defines efficient energy scenarios which are coherent with political goals. For example, we want to reach certain renewable targets, we want to reach reduction of CO2 emissions and so on. So they, within this long-term energy planning, well, other goals are, for example, the integration of renewable vehicles and so on. And as a result of this long energy planning, one of them or few of them are, you get these scenarios. Okay, how to reach these targets, we should have this generation matrix evolution within the next 20, 30 years. We should have, okay, in case that the demand grows above average, this is how we meet the demand. In case of, for example, we're talking about the integration of green hydrogen. Okay, in this case, this is how we should meet from a cost optimal perspective these plans to integrate green hydrogen and so on. And another new thing defined, at least for us in Chile, is the definition of renewable hubs, which means in Chile we have lots of resources, but that are allocated, for example, if I'm going to go a little bit back, but are allocated in isolated area in the north, where the main load is here in Santiago and perhaps a little bit in the south. Also towards the mountain, yes, we have lots of renewable potential. And the thing is, for renewable energies to be integrated there, it's not easy because you will need to build 100 kilometers long transmission line. So one single project won't build this transmission line because it's expensive. And to make stakeholders, generation companies work together and build together such a long transmission line is also difficult. So what happens is that according to our new regulation, the Ministry of Energy defines this type of renewable hub, where when it identifies a nice potential, the transmission line that is required to get to this place with high potential of renewable energies, it's done automatically by the government, not by private investor. And this way, we hope to foster the integration of these renewable energies, especially in isolated areas, long where even the main transmission line is located. So from that, I'm going to go back then. So this is the long-term energy planning, and then as a next step, the ISO makes a proposal. It makes first a diagnosis of the transmission line and makes a proposal. Okay, this is how we should expand our network. After that, the different stakeholder and any person or entity that wants to also propose expansion projects can also have the possibility of proposing these projects. And our energy regulator takes this proposal from the ISO and from private companies and determines a preliminary expansion plan. Yes, and after that, every entity can make observation of this plan and can say, I agree with this, I don't agree with this, and the energy regulator takes these observations and defines a final expansion plan. If there are still issues with the final expansion plan, for example, a generation company says, look, I don't agree with this plan, you can get the discrepancies to to an entity called expert panel. I'm getting a little bit ahead of my presentation now. One issue, how this energy regulator defines the expansion plan, you must understand that for a real-world power system, it is difficult to formulate an optimization model, solve the optimization model, and say, okay, this is expansion plan. It's not as easy because there are many issues, many things that you need to, many details that you need to take care of. So what happens now is that projects, so is defined by our regulatory framework, is that the projects are economically evaluated in a sequential approach, which means one by one. Let's say, for example, from here, you have the energy regulator have a list of 50 projects. They know how the system works, so they can say, okay, this project, I know from feeling, from expert knowledge, I know this project is good because it helps relieving congestions in the next 5 years, for example. So they evaluate this project, and literally they they simulate the operation of the system in the future with and without that project. And if that project, for example, up from a certain year, the cost of the project is less than the economic benefit that it has, it's incorporated in the plan. And then they come to the next project. So this project is already fixed, and then they take the next project in the list where they think, oh, this could be beneficial, and they evaluate it. If the economic evaluation is good, okay, it is incorporated in the plan. Otherwise, it is rejected. It is discarded, sorry. And so, in a nutshell, of course, our plan is being developed from an economical criteria point of view. There are other criteria, of course, for example, security and so on. But, of course, there is no portfolio evaluation, because we all know that the 2 or 3 projects can have synergies between them, and together they may make sense, but if you evaluate them individually, it may make no sense. So this procedure may lead to suboptimal solution, and it's some sort of a headache that we have, because we're not evaluating portfolios of projects and taking advantage of the synergies between them, but evaluating them in a sequential way. So after this energy regulator makes the final expansion plan, as I said, people or entities can complain, and this is something made in Chile, I believe. I haven't seen that elsewhere, and which is called the expert panel. The expert panel is an expert panel from there are 7 experts that are independent from any specific companies, and they decide every discrepancy between that occurs in the system within the actors in Chile, and their resolution is binding. So if there are discrepancy with the expansion plan, this expert panel reviews it and say, okay, I give the energy regulator the reason, or no, I give this company the reason, and this is binding. And after that, the final expansion plan is made by an executive order of the Ministry of Energy. So once the executive order is issued, the problem we had in Chile was that to build a transmission line, sometimes a non-governmental organization or any private person would could go to the justice and say, look, I don't like this plan. It's against my rights, and many projects were judicialized and went into and the justice stopped the building of this project, and that was a big issue in Chile. So to avoid this issue, in Chile we came up with something that it looked a very nice idea actually, which was an additional process being developed by the Ministry of Energy, where they say, okay, we need to build a transmission line from A to B. Okay, we are going to define more or less in detail, but not that much detail, the right of way. So it should go through this path. And within this process, non-governmental organizations and local communities and so would be invited to follow this process, to get to know the project, to be involved, actively involved, and take their concerns before defining this narrower right of way. And the idea, I think, if you listen to that, it makes sense. It makes sense because in that way you reduce the risk of delays due to judicialization and so on. And then after this narrower right of way was determined, you make the auction, which is led by the ISO, where you invited any company, internationally or national transmission company, to bid and build this transmission line. So this is actually how our current process works, and we have some issue. First, in practice, this process here until the executive order is issued takes a year. Takes a year from the beginning until the end. But the problem is that since you may have discrepancies, what happens was that it took longer. It started taking longer than a year, and this is actual date from the process that in the year 2020 that started with the long-term planning from the Ministry of Energy in September, October 2019, and the discrepancies were only resolved by the expert panel in May, June 2021, meaning 1.5 years later. But how does that work? Because we have this process by law. It's a yearly process. So what happens is that after the process for next year, for 2021, started already, we were still unsure of the expansion plan from the year before, which makes a huge problem because of the uncertainty. The private company would say, okay, I need this transmission line or this transformer to be built, but I'm not sure if it's going to be approved by the process before. Should I propose it again this year? And it's not that you just propose a project to the energy regulator. You need to make detailed studies justifying why are you presenting this project to be built. So it takes also time and economic resources from the companies to present those proposals. So these delays started to giving us huge headaches, and also something, and this is perhaps one big issue that we have, how a nice idea that but without the proper regulatory framework can be turned into a bad idea, is that here everything is connected. The Ministry of Energy defines the generation scenarios for the future, energetic scenarios in the future. The ISO is also involved. They know the system. They know exactly where are the bottlenecks, and they're supposed to work together with the energy regulator. The problem is that it was in in the regulatory framework, it was never explicitly said that they must use the same scenarios. So what happens in Chile is that since they didn't say that, the energy scenarios defined by the Ministry of Energy were different than the energy scenarios that the ISO took, because our ISO said, well, I know better. I know my network. I'm the expert in the network, so I know where it's heading. And they were different from the energy scenarios defined by the energy regulator, because they also know better. And the problem was that they were really different, and not slightly different, but really different. For example, this is just in a small example of how different they both can be. Here at the right is the additional capacity for the process in 2023, I believe, up in the year 2041. And here you see that the energy regulator counts on the incorporation of diesel of 1.2 gigawatts. It counts on a very large incorporation of aeolic energy in one of the scenarios, and batteries, 10 gigawatts of batteries in another scenario, but throughout all scenarios. And the ISO didn't think that we need diesel at all. And batteries, it's only in the best case 1.7 gigawatt for year 2041, and in the worst case, the energy regulator says, okay, 2.5 gigawatts of batteries. In the best place is 10 gigawatts of batteries. So, of course, if you have such a different generation expansion, and you cannot come with coherent expansion plan, because you are projecting different networks. And this was a problem in us, because the idea was very nice, but since it wasn't explicitly forced that all of these entities, the Energy of Ministry, the ISO, and the Energy Regulator, should take similar, not the same, but at least similar scenarios, they took very different. So in principle, what the ISO proposes may get, and it was the case, was rejected by the energy regulator, because they were seeing two different network paths. And that was another issue that we had in Chile that we are fully aware of. And the other issue was the right-of-way process. The right-of-way process sounded very good. I liked that idea a lot when it came as a law, but after the first experience, in theory, this process was expected to last 2 years. 2 years, and then after 2 years, you really define more or less where this transmission line should go through. But the problem is that in practice, it took even more than 4 years for each process, and took lots of resources. And in my opinion, it was that the Ministry of Energy didn't have the expertise to conduct such a process. And the thing went so critical that nowadays, if we know, okay, this line must be built, we know it's critical because it's long, it may go through or very nearby a national park or where local communities live. They said, okay, by exception, this new line is not going to go through this process anymore, but it's going to go all the traditional way. The company that conducts this process, that wants to bid, needs to do that. And it shows that unfortunately the idea was very interesting, but in practice it led to very poor results. And now we must deal with okay, what are we going to do in the future, because the underlying problem is still there. How can we accelerate the process of getting the right of way, and that the projects are not being judicialized? And I think this is one of my last slides. Another issue that we have is that our regulatory framework does not explicitly foster the use of short-term expansion alternatives to deal with congestion. And similar as the way the energy scenarios are defined, if it's not explicitly stated how they should be done, in practice the companies or the energy regulator, they won't use it. So what happens is that our energy regulator is not considering any or only the most very few short-term expansion alternatives. And nowadays there are plenty of evidence that flexible technologies may play a key role for achieving a time-effective increase of the transmission capacities. What are these short-term expansion solutions? SIPs, these system integrated protection schemes, they can be built very fast and help alleviating congestions with minimum environmental impact, so that it should not be very too problematic to be built. Flexible AC transmission system like HVC, STATCOM, TCS, UPFC, and so on. Upgrade or reinforcement of existing access, for example, reconductoring, voltage operating, DLR. DLR is not a requirement explicitly in Chile, but nowadays with the technology, every line should be built with a DLR already incorporated. Other control actions, for example, demand response, line switching, they're not being considered within the expansion planning process. So if they are not considered explicitly there, then this solution it's not going to be viable, visible. Other issues, and I think this is my last slide. Every year there are unsuccessful auctions with no tenders, and we identify that among others, the energy regulator has its own belief of, okay, what is really the cost of building a transmission line. So they set a cap that it's apparently lower than what the rest of the transmission companies believe. So we have this is a very, very big issue, because if you have a tender that that is unsuccessful, you lose at least 6 months or even longer because of the whole process. So in our case, it is important to, if the energy regulator is not fully considering the prices or the cost of building a transmission line that are coherent with what the industry believes, then the whole expansion plan also changes. And other relevant issues that we have, I believe, it's also everywhere in the world is granularity of the expansion planning models, tools, the endogenous incorporation of distributed energy sources. I heard about this PhD presentation today. How are we conducting distribution expansion and transmission expansion? How is that? How can be? Because of course they are nowadays not alone, especially with active green. That's the first time I heard that term, active green distribution networks in the future. So they should be somehow considered within this expansion project. Power to X, new energy vector, and especially extreme weather events within the planning approach are also some of our issues, our challenges that we have, and that we hope to solve, at least to address in a proper way in the near future. So in Chile, at least, there's an urgent need to adjust the regulatory framework to reduce the contraction lead time, and starting from the planning process itself. Because to build one transmission line, it takes at least or 5 to 10 years, and any delays can lead to very big consequences. Thank you very much.
Thank you, Dr. Alvarez. Our next speaker is Pablo Ochiza. The floor is all yours. Thank you.
Thanks everyone for attending this presentation. I'm going to show you my research on the topic of machine learning-based column generation with applications in transmission expansion planning. So, in the context of large-scale integration, Is okay? Yeah. Sorry. So in the context of large-scale integration of renewables, the planning of a transmission system is getting a little bit more complex because now we are integrating new technologies, we're integrating more variability and uncertainty into the system. So in order to be able to solve this complex optimization problem, we need new, more creative or more efficient algorithms. The common strategy for solving, for example, transmission planning, which is a mixed integer optimization problem, is algorithms like branch and bound on the composition algorithms such as vendors or column generation. However, these algorithms, though they are efficient, they still suffer from non-polynomial complexity because of the mixed integer nature of the problem itself. Recent developments in artificial intelligence, machine learning, is showing promising results though to accelerate and improve the efficiency of these algorithms. So in this context, we see three main paradigms. The first one is end-to-end learning, where the machine learning agent treats the system as a black box, meaning it wants to relate the inputs with the optimal outputs and learn from this data. This approach is quite simple and very useful for linear problems and even nonlinear problems, but for mixed integer problems it is not a really good approach, and even for linear and nonlinear problems, you often cannot guarantee optimality of this approach. So the second alternative is reinforcement learning, where an agent learns from continuous interaction with the system and through appropriate reward signals. This also is very useful for a large variety of problems, not only in transmission planning, but is not, also cannot guarantee the optimality of your solution. And the last approach, which is algorithm-specific learning, learns to accelerate the convergence, the efficiency of known optimization algorithms. And here is first very flexible because depending on the problem you want to solve, you can work with your preferred algorithm. And second, it can be designed to guarantee optimality. So this is a really nice thing that we care about in transmission planning. This is the particular problem we want to solve, the transmission expansion planning problem. This is an investment and operation problem. You want to minimize both variables, and the investment variables are binary because you have to decide whether or not to invest in one project, so 0-1 kind of decision. And where you have some operational constraints which are in continuous space, and some investment constraints which are binary for the nature of these variables. And these constraints are complicated because since we are planning for a large time horizon, so many years into the future, these kind of constraints make sure that the plan is coherent in time. So if you decide to invest in a new transmission line or storage project in the first year, this project has to be part of the system in the following years. So to do that, you use these kinds of constraints. However, these constraints link the decisions together over the years, so you cannot decompose the problem into individual years. You have to solve the whole problem right away. Or it would be the case were not for the decomposition techniques, which can help you with those sort of constraints. So we decide to use the composition technique to avoid this problem of complicated constraints, and we use the column generation algorithm. With the column generation algorithm, now we have a master problem and one sub-problem for every year, so it's decomposed into many years. And in the sub-problem, you have the operational constraints, and in the master problem, you have this complicated investment constraint, which you are relaxing into the sub-problem through this dual value pi, which is passed into the objective function of the sub-problem. So now the sub-problems are free of this complicated constraint, and you can solve it in parallel. 1 year individually. Once you solve these sub-problems, you will get a solution of the investment variable set, which is one of your binary variables. And this feasible solution, which we call a column, which has kind of this shape, like for example, if you have 6 projects, it will be a vector of 6 with zeros and ones. You find a solution from the sub-problem of a feasible investment plan, and pass it to the master problem, and the master problem is a combinatory problem where you choose the best columns you have generated so far, and you keep going on iteratively, improving every time the optimality graph and the quality of your solution. Now this is a very nice algorithm, very efficient. However, the sub-problems are still of MILP nature, and thus they are a bottleneck for the efficiency of the algorithm. Meaning, even though they are going to be solved faster because they are decomposed into many years, these sub-problems still can take a lot of time to solve. And if you could reduce this time, then the algorithm will go on much faster. So what is our proposal for accelerating this column generation algorithm in transmission planning? So originally you are solving your yearly sub-problems where the investment variables are of binary nature, integer variables. We are proposing that you could relax the nature of this variable into continuous values. Now, from solving this problem with relaxed nature, you are not going to get useful solution, not feasible solution, because you cannot invest in 0.6 transmission line or 0.3 storage device. That is not a solution that makes sense. However, our hypothesis is that from this solution you can learn important things to try to predict which would have been the actual binary solution, the 0-1 value. So we are passing relevant economic features from the LP solution to a binary classifier that fixes the investment values to either 0 or 1. And from there, we are solving now a fixed subproblem where a set is fixed to the prediction of the classifier. And this does give you a valid column, a feasible column for the column generation algorithm, which can keep going on with the iterations. So in order for this proposal to work, we have to design good features that give you high enough accuracy. If your agent is accurate enough, then this proposal is going to be very useful for reducing the computation time. So one of the first features we thought about was the earnings of the line. Now, a transmission line makes money by selling the marginal price difference across the nodes times the power that is flowing through the line. So you can calculate the revenue of a transmission line by this nice formula where you have the marginal price difference across the nodes times the power flowing through the line, and you sum that across all the time horizon of the subproblem. And we are comparing that to the investment value, which is this pi value, if you remember, in the subproblem. Now we are summing them because pi is a negative number, but what this operation does is just comparing the revenue with the cost. So this is negative and this is positive. We are also considering storage projects as transmission expansion assets. And here we have a similar feature, also earnings of the project, but storage makes money by doing arbitrage between the cheapest hours and the most expensive hours. They withdraw energy from the system when it's cheap, and they put it back in the system when it's expensive. So the revenue of the storage will be calculated just as the sum over time of the marginal price times the power injection, which can go both ways, can be positive or negative. And we also compare that with the investment of the project, investment cost, which is this pi value. Another feature we are using is the usage ratio. This is much simpler feature, more straightforward. So it basically tells you how much of the capacity of this project you are using out of the maximum. So for a line, it will be the flow of the line divided by F max. And for storage, it would be the power discharge of the line divided by the max capacity of the storage. Now there is another feature, which is the positive and negative capacity duals. Now, when a line is congested, meaning that is reaching the maximum capacity of the project, this constraint of max capacity is going to be binding, and this mu value will be different than 0. And the value of mu can give you a hint on what is the monetary value you are losing for not expanding further this line. So if you sum also these duals, we can go in the positive or negative sense. You're going to get new features for storage and line projects. They work in the same way. Now, from all of these features, we are trying to make a prediction whether the investment should be fixed as 0 and 1. So then we are just training a binary classifier. This will work something like this. For example, here the linear solution was 0.89. And the earnings are positive, the economic benefit is positive and quite large compared with the others. So most likely the classifier will identify this as a valuable investment and will fix this as 1. In other example here, the linear solution was 0 and the economic benefit was negative, so more likely than not the investment will be 0. and you have all of these other features which help you to identify the patterns in investment in the subproblems. So, what problem do we want to solve? We are working with this 38 bus system, which considers a mix of thermal and renewable generation, 20 expansion projects, 10 storage investment projects, DC power flow formulations, 12 representative days, and 15-year planning horizon. And we are making different scenarios from combination of these inputs, demand growth, renewable capacity growth, and storage investment, to try to train in different scenarios from the ones we are going to be solving. For the classifier, we are using random forest, which is an ensemble of the decision trees. And through majority voting, it decides on a binary class prediction, but it also gives you some more information, because not only gives you the 0-1 prediction of the classifier, it also gives you a probability of the prediction, which is a degree of confidence of how sure it is of this prediction. Now we can do a nice trick to put a confidence threshold into our algorithm, and only fix the values which are the agent is really sure about the class. Like if the threshold is above 0.9, for example, we are fixing the class as 0. Below 0.1, we're fixing the class as 1 and then 0. And anything in between, we will keep as integer in the subproblems. This means that once again we are solving mixed integer problems, which was the whole point to avoid, but this will be a mixed integer problem of reduced size, because now we have less binary variables, and provided that the majority of the variables are being fixed, this could result in a significant time reduction. So what are the results we are getting with this methodology? We are going to be seeing two kinds of results. First, the classifier accuracy, measured without confidence threshold and with 90% confidence threshold. And then we will be looking at the computation time, also without confidence, 90% confidence threshold, and we will be comparing that with the original column generation algorithm without the classifier. Here you can see a summary of the accuracy of the agent across 10 different scenarios. For the all data points, meaning no confidence threshold, the accuracy is an average of 90.5%. So the agent performs pretty good at predicting the mixed integer solutions from the linear relaxation. However, if you use the confidence threshold technique, 90% confidence threshold, you can improve the accuracy a lot to 98%, which is much better. And you are not missing much variables here, like 80% of the variables are still inside this confidence threshold. So most of the variables you are going to be fixing, but you can guarantee that you have a really high accuracy in this prediction. This is now the computation times we are seeing across also, in this case, 11 different scenarios. And we can see that the agent with the classifier in blue is performing better than the column generation algorithm in most scenarios, where the time saves can go up to 48%, almost twice as fast as the column generation algorithm, with optimal solution. This is achieving the same quality of solution as the column generation algorithm. However, there is some scenarios where the agent is performing worse. For example, this scenario number 7 or scenario number 4. These cases happen when the classifier is not accurate enough. So even though you are taking less time on every subproblem, the quality of the column you are generating is not good enough to keep moving forward in the column generation algorithm. So you end up with the same quality of solution, but it takes a little bit longer. However, in most cases, the time saves are positive and they are quite good. For example, here, a problem which was solved in almost more than an hour, 70 minutes, you could solve it to 40 minutes, less than 40 minutes, in the same quality of solution. Now, if we use confidence threshold, things improve a lot. First, the time saves go up to 52.7%, so improve a little bit. And also, the worst case performance is now way better. Like the difference between column generation and the classifier is much smaller, so the risk you are taking is less too. Now we are going to be looking at an application in the Chilean study case. So the first study was done in 38 bus system, and we wanted to try the algorithm in something more realistic, more complex. So I'm going to be skipping this one because Ricardo already went into depth of the Chilean system. But you have to know that our model has 287 buses, so it's much larger. and we are using real-time data for the model, so it's more significant, the results we're going to be looking here. In this case, the average time saves was 37%, and we did not see any scenario where the agent with the classifier took longer than without the classifier, so it's much better already. And in the best cases, the time saved was very significant. For example, here, the problem was solved in about 20 hours with the classifier, and without the classifier, you took longer than a day to solve the problem, like over 30, almost 35 hours. So it's a really significant time save. Here is an example of the best case with a 56% time save. Here you can see that the sub-problems are solved way faster than with the classifier solved way faster than the column generation one. So quickly you can improve the objective function faster and reach a solution which is of equal quality than the column generation algorithm much faster. This, however, was one of the worst cases. Still, we see time saved here, but it's not as impressive as the previous one, with 11%. In this case, the improvement was quite fast, but after that, the agent was getting stuck, so we switched back to the column generation algorithm, and in few iterations, we reached optimality here, faster than the original column generation algorithm without classifier, but the improvement was not as significant because the accuracy was not as good as the previous case. So in conclusion of this research, it is possible to make very accurate predictions of the mixed integer solution from a linear relaxation, which can be integrated into the column generation algorithm to improve the convergence speed of the algorithm. And an appropriate confidence level can be used for the classifier in order to improve the accuracy and the efficiency of this proposal. So thanks a lot for your attention. This was my presentation.
Ladies and gentlemen, we have about 5 minutes for Q&As. If you have any questions, please go ahead.
I have a question for Professor Alvarez, more along the lines of is the regulator that you mentioned primarily an economic regulator or not? Because the regulator is trying to second guess ISO, which has the technical expertise, and then you get into conflict. So what is the primary role of the regulator? Is it economics or not?
It's to define the it's to define the technical guidelines that rules the ISO. For example, it defines just like a very simple the minimum and maximum voltages. The energy regulator, among others, defines the expansion plan, defines the technical norms, it is in charge to determine whether or not the market, for example, the market for ancillary services has enough competitions or not. It defines the products that are being sold in the market for ancillary service. So it's in charge of technical norms, and we have the law, the regulatory framework. He proposes the regulatory framework to take the law down to practicality.
Maybe my question requires a longer discussion with you. Another quick one: is the regulator subject to ministerial directive or not?
Pardon?
Is the regulator subject to
Yes.
ministerial directive? So the minister could override the regulator or not?
Yes, it's the Ministry of, we can say the regulator is seen as the technical branch or the technical entity that feeds information to the Ministry of Energy. So the Ministry of Energy is more politics, so it has a technical branch which is the energy regulator, but it's under the under the Ministry of Energy. Yes.
Thank you. I don't want to take up the time. My issues and discussion is a longer one with you.
Yeah, we can discuss that afterwards. Happy to. Thank you.
More questions?
So, in great case studies, just a quick question: does Chile market have FTRs?
FDRs, I think we do not have FDR, right?
Distributed renewable?
No, FTS, farm transmission
Financial
rights.
transmission.
Financial
Financial transmission rights.
Yeah, it's congestion revenue rights or financial.
Because those can give you the signal of which lines are getting
Which we are
congested.
using that. in the
Yeah,
LFP
it's similar to
section.
the. But not.
You
not
design one of your features.
Yeah, one of my features is very similar to what you would see in congestion revenue rights. It's just the marginal price difference times the flow.
But that would happen only in case of if there are congestion or losses.
Yeah.
Can I ask a question? One question for Professor Alvarez. You mentioned that the projects are evaluated one by one.
Yes.
And I think that's a little bit problematic because
It is.
that's more like a greedy approach. You're choosing one project and you see if it is good or not,
Yes.
rather than looking at the whole system and coming up with a global optimal solution.
Exactly.
Yeah.
Yeah.
And yeah, well, I think the process you have in Chile is much better than what we have here. Usually for transmission lines, it takes like 10 years or so. I've seen
We all have
that
the same
much, yeah.
problems.
But
Yeah.
you have less than 4 years, 3 years, I guess, or 2 years here.
And I would
And
say
it still
that the
comes like-
minimum 5 years. I mean, if we're lucky, if the line is not so long, yes, but it's a long process. It's a long process. I
And
think
we
between
have-
5 and
yeah,
10. Yes.
Yeah. Okay, so that's pretty similar. And I think we have lots of similarities with the geographical span we have. You are north, south, we are east. So if you rotate Chile for, like the dimensions, I just checked that, they are exactly the same.
Yes.
So if you rotate it 90 degrees, that will become Canada, and you have to widen it a little bit too.
Yeah. Interesting.
Yeah, thank you.
Sure.
Just a comment like in today's context, I don't know whether in real systems they do carry out such centralized optimization and unified selection of optimal set of transmission expansion. Those are indeed case by case basis. Like in Ontario also we do case by case basis. This is each tie lines are determined and then projects are. So I'd like to hear from you.
Yes, indeed, because it's as you mentioned, the details in the model must be so big that it's difficult to define an optimization problem and solve it and so on. However, in my opinion, there could be a way where a centralized optimization model provides you some guidelines into an expansion portfolio, where you, instead of evaluating projects one by one, you evaluated a group of projects that may have synergies among them. For example, I know that in Germany they don't run an optimization formulation, but they do have something what is called the heuristic nets planning. So somehow with genetic algorithms, I know that they do this. They identify different expansion proposals, perhaps not optimal, but efficient. And these proposals are then evaluated economically by either the transmission system operator, what they have there, the TSO, or the energy regulator that also takes some role in the expansion plan. But it's still, in my opinion, good to evaluate a portfolio, different alternatives, but together, not one by one, as is in the case of Chile. Is that, did I answer your question?
Yep, thank you.
Good.
Okay, perfect. Thank you so much, Dr.
Thank you.
Alvarez and Pablo, for your wonderful presentation and sharing some great insights with us. And now we will take a quick 5-minute break before we move on to our next guest speaker for today. Thank you. Thank you so very much.